Hey guys, welcome back. Tonight, we will be exploring one of the most catastrophic and awe-inspiring events in the universe, the death of a star. This isn't just an abstract astronomical phenomenon happening billions of light years away. This is a journey that puts you right in the path of stellar destruction, experiencing firsthand the incredible forces that reshape galaxies and forge the heavy elements that make life possible. You'll discover why no amount of preparation, technology, or distance could save you from the cosmic violence unleashed when a massive star reaches the end of its life cycle. From the initial warning signs to the final cataclysmic explosion, you'll witness the raw power of nuclear fusion gone wild, and understand why stellar death represents both creation and annihilation on an unimaginable scale. If you like the content and want to support the channel, be sure to subscribe. You are aboard the research vessel Prometheus, stationed exactly 50 astronomical units away from the massive blue supergent star, designated HD 2000 star, designated HD 2000, which your team has been monitoring for the past 18 months. At this distance, you feel relatively safe. After all, 50 places you well beyond the orbit of Pluto in our own solar system. The star has been showing signs of instability for several years, and you've been sent here as part of an international scientific mission to observe what your models predict will be one of the most spectacular stellar deaths in recorded history. You stand in the observation deck, looking out through the reinforced transparent aluminum viewport at the brilliant blue-white star that dominates your view. Even at this tremendous distance, HD 2847 appears as a blazing disk rather than a point of light, its surface seething with violent convection currents that you can observe through the ship's powerful telescopes. You feel a mixture of scientific excitement and primal unease as you realize you're watching a star that outmasses our sun by more than 40 times struggle through its final days of life. Your colleague, Dr. Sarah Chen, approaches with the latest spectroscopic analysis, and you see concern etched across her features. The star's core temperature has been climbing steadily over the past few weeks, now approaching 2 billion Kelvin, hot enough to fuse silicon into iron. You feel your stomach tighten as you remember your stellar evolution training. Once a massive star begins producing iron in its core, it has only hours or days left to live. You review the data streaming in from the automated monitoring probes positioned at various distances around the star. The readings show that HD 2847's luminosity has increased by 12% in just the last 72 hours, while its surface temperature has paradoxically begun to drop. You recognize these as classic signs of a star in its final death throes, the core collapsing while the outer layers expand and cool. Dr. Chen explains that the star's core has grown to approximately the size of Earth, but contains more mass than our entire sun. You try to comprehend the incredible density involved. A teaspoon of core material would weigh as much as a mountain on Earth. The nuclear fusion reactions that have powered the star for millions of years are becoming increasingly unstable as heavier and heavier elements accumulate in the core. You feel the ship's artificial gravity generator hum slightly as it compensates for the increasing gravitational pull from the dying star. Even at 50 HD 2847's immense gravity is beginning to affect your vessel's trajectory. The star's mass warps space-time so severely that light itself bends around it, creating gravitational lensing effects that you can observe through the ship's instruments. The captain announces over the intercom that all non-essential personnel should secure themselves for potential gravitational fluctuations. You make your way to your station in the primary laboratory, where banks of sensors are recording every aspect of the star's final moments. The electromagnetic readings show massive solar flares erupting from the star's surface with increasing frequency and intensity. You notice that the star's magnetic field is becoming chaotic and unpredictable. The field lines, normally organized in relatively stable patterns, are twisting and reconnecting violently, releasing enormous amounts of energy. These magnetic reconnection events are producing X-ray and gamma-ray bursts that would be lethal to any unshielded life form within several light years of the star. Through the ship's communication system, you receive updates from the other monitoring stations positioned around HD 2847. The readings are consistent. Every instrument confirms that the star is approaching core collapse. You feel a chill as you realize that you're about to witness an event that releases more energy in seconds than our sun will produce in its entire 10 billion year lifetime. You check the ship's radiation shielding systems for the 100th time, knowing that when the star explodes, the initial burst of high energy radiation will travel at the speed of light, giving you no warning before it arrives. The ship's magnetic deflectors and neutronium composite hull are designed to protect against the most extreme cosmic radiation. But you're about to test those systems beyond their intended limits. The stellar wind from HD 2847 has been steadily increasing, and you can see its effects on the surrounding interstellar medium. Vast clouds of gas and dust that have drifted in the star's vicinity for millennia are being pushed outward by the increasingly violent stellar wind. You realize that this wind, traveling at thousands of kilometers per second, carries with it the heavy elements forged in the star's core over millions of years. Dr. Chen points to a disturbing trend in the neutrino detection data. The star is producing an enormous flux of neutrinos as nuclear reactions in its core become increasingly exotic and desperate. You know that neutrinos normally pass through matter as if it weren't there. But the flux from HD 2008 is so intense that it's actually affecting the ship's particle detectors. This neutrino bombardment is a clear sign that the star's core is on the verge of catastrophic collapse. You feel the ship shudder slightly as it automatically adjusts its position to compensate for the star's changing gravitational field. 82,847's gravity is now strong enough to noticeably bend the trajectories of nearby asteroids and cosmic debris, creating a complex and dangerous navigation environment. The ship's AI continuously calculates safe trajectories while monitoring for incoming debris, accelerated by the star's gravity. The temperature readings from your instruments show that the star's photosphere is now cooling rapidly, dropping from 40,000 Kelvin to less than 20,000 in just a few hours. You understand that this cooling occurs because the star's outer layers are expanding dramatically as the core contracts. The star is literally tearing itself apart as gravitational forces overwhelm the nuclear fusion that has maintained its stability for millions of years. You observe massive stellar prominences erupting from HD 2847's surface, some extending millions of kilometers into space before falling back toward the star or being swept away by the increasingly violent stellar wind. These prominences contain more material than hundreds of Earth-sized planets, and they're being hurled into space at velocities that would allow them to escape most stars' gravitational wells. The ship's seismometers detect gravitational waves emanating from the dying star as its core undergoes violent convective motions. You feel awed by the realization that space-time itself is rippling around you as the star's core density approaches that of an atomic nucleus. These gravitational waves carry information about the incredibly dense and hot conditions in the star's interior. Conditions so extreme your radiation detectors show a sudden spike in gamma ray emissions as the star's magnetic field undergoes a violent reconfiguration. The energy release is equivalent to the total output of thousands of stars like our sun. And it's all happening in a matter of minutes. You check your personal radiation dosimeter and are relieved to see that the ship's shielding is holding. Though you know this is nothing compared to what's coming. You notice that the star's rotation is accelerating as its core contracts, following the same principle that causes figure skaters to spin faster when they pull in their arms. 847 surface is now rotating at nearly 1,000 kilometers per second at the equator, creating enormous central forces that contribute to the star's instability. The combination of gravitational collapse, rapid rotation, and intense magnetic fields creates a chaotic environment where the normal laws of stellar physics break down. Through the ship's telescopes, you can see that the star's surface is becoming increasingly mottled and unstable. Convection cells, the size of Earth's orbit, transport superheated material from the interior to the surface, where it cools and sinks back down in a violent cycle. You realize that each of these convection cells contains more energy than humanity has ever produced, and there are thousands of them covering the star's surface. The spectroscopic data reveals that HD 847 is now fusing silicon into iron at an unprecedented rate. You feel a sense of impending doom as you remember that iron cannot be fused into heavier elements in a way that releases energy. Instead, fusion beyond iron actually absorbs energy, hastening the core's collapse. The star is literally poisoning itself with its own nuclear waste products. You receive an urgent message from the monitoring station, positioned closer to the star, at only 20 O distance. Their readings show that the stellar wind has suddenly intensified dramatically, and they're detecting exotic particles that shouldn't exist under normal stellar conditions. The message cuts off abruptly, and when you try to re-establish contact, you receive only static. You feel a chill as you realize that something has happened to your colleagues. Dr. Chen shows you the latest gravitational wave data, and you see a pattern that makes your blood run cold. The waves are showing a characteristic signature that theoretical models associate with core bounce. The moment when the collapsing stellar core reaches nuclear density and suddenly reverses direction, sending a massive shockwave outward through the star. You know that core bounce is the precursor to supernova explosion, and it appears to be happening now. The ship's AI announces a red alert as it detects an enormous burst of neutrinos from HD 2847's direction. The neutrino flux is so intense that it's actually heating the ship's hull through direct particle interactions, something that should be physically impossible given neutrinos' extremely low interaction probability. You realize that you're experiencing the neutrino burst that precedes a supernova explosion by several hours. the last warning you'll receive before the light and shock wave arrive. You feel the artificial gravity fluctuate as the ship's generators struggle to compensate for the wildly varying gravitational field from the collapsing star. 82,847 has now collapsed to a diameter of less than 20 kilometers, while retaining more mass than our entire sun. The resulting gravitational field is so intense that it's affecting space-time in ways that your instruments can barely measure. Through the ship's most powerful telescope, you watch in fascination and terror as the star's outer layers begin to fall inward toward the collapsed core at velocities approaching 20,000 kilometers per second. The infalling material carries the kinetic energy equivalent to billions of nuclear weapons, all focused on a core smaller than a large city. You understand that when this material strikes the incompressible nuclear matter of the core, it will rebound outward with unimaginable violence. The electromagnetic spectrum readings from HD 2847 show emissions at frequencies that shouldn't be possible under normal stellar conditions. You're detecting gamma rays with energies in the tera-electron-volt range, produced by processes so violent that they accelerate particles to nearly the speed of light. These gamma rays are a harbinger of the electromagnetic catastrophe that will accompany the star's explosion. You notice that the star's apparent size is increasing as its outer layers expand, but its total luminosity is actually decreasing as the surface temperature drops. This paradoxical behavior is characteristic of a star in its final moments before explosion. The core collapse causes the outer layers to expand and cool even as unimaginable energies build up in the stellar interior. Your dosimeter begins clicking more rapidly as high-energy particles from the star's increasingly violent stellar wind reach your location. Even at 50O, you're beginning to experience radiation levels that would be dangerous during extended exposure. You realize that any planet within hundreds of O of HD 2847 would already be experiencing a mass extinction event from the pre-supernova radiation alone. The ship's captain orders all personnel to emergency stations as the gravitational wave detectors register increasingly violent oscillations from the star's interior. You can actually feel the ship vibrate slightly as gravitational waves with frequencies in the audible range pass through your location. The fact that you can physically feel the warping of space-time itself fills you with a profound sense of cosmic insignificance. Dr. Chen's latest calculations show that the star's core has reached a density of approximately 10 to the 15th grams per cubic centimeter, approaching the density of an atomic nucleus. At this density, protons and electrons are being crushed together to form neutrons, releasing enormous numbers of neutrinos and causing the core to become effectively incompressible. You understand that this marks the point of no return. The core can collapse no further, and the infalling outer layers must rebound outward. You observe through the telescopes that HD 2847's has become incredibly twisted and complex, with field strengths approaching 1 trillion times Earth's magnetic field. These intense magnetic fields are channeling the star's plasma into narrow jets that extend far into space. And you realize that if one of these jets were pointed in your direction, no amount of shielding could protect you from the focused beam of relativistic particles. The neutrino detectors register a sudden massive spike that saturates the instruments. You know that this indicates the moment of core bounce. when the infalling stellar material strikes the neutron core and rebounds outward, creating a shock wave that will propagate through the star's outer layers at thousands of kilometers per second. The supernova explosion has begun, though its light won't reach you for several more hours. You feel a mixture of scientific excitement and existential terror as you realize you're witnessing one of the most violent events in the universe. The shock wave now propagating through HD 2847's outer layers carries more energy than our sun will produce in billions of years, and it's moving outward at a significant fraction of the speed of light. When it reaches the star's surface, it will accelerate the outer layers to velocities of tens of thousands of kilometers per second. The ship's radiation alarms begin sounding as high-energy gamma rays from the star's interior processes reach your location. These gamma rays are produced by the collision of the shock wave with dense pockets of material in the star's outer layers, creating temperatures and pressures sufficient to trigger nuclear reactions that don't occur under normal stellar conditions. The ship's shielding reduces the radiation to manageable levels, but you know that this is only the beginning. You check the ship's escape trajectory calculations and feel your heart sink. Even at maximum acceleration, you cannot outrun the expanding shell of stellar debris that will eventually reach your location. The best your ship can do is position itself to minimize exposure to the most dangerous components of the explosion. But escape is impossible. You're going to experience a supernova explosion at close range, regardless of any evasive action you might take. Through the communication system, you hear increasingly frantic reports from automated monitoring stations positioned around HD 2847. The stations closest to the star have already gone silent, presumably destroyed by the intense radiation and particle bombardment that precedes the arrival of the shock wave itself. You realize that you're watching the destruction propagate outward from the star like a wave of cosmic annihilation. Dr. Chen points to the spectroscopic data, showing that the star's atmosphere now contains elements that don't exist naturally anywhere in the universe. Exotic isotopes created by the incredible neutron flux generated during core collapse. These elements have half-lives measured in seconds or minutes, and their very existence indicates that nuclear processes in the dying star have moved far beyond anything that occurs during normal stellar evolution. You observe that HD 2847's luminosity is beginning to increase dramatically as the shock wave approaches the star's surface. The energy being released is so enormous that it's actually affecting the local gravitational field, causing minute but measurable changes in your ship's trajectory. You're witnessing the moment when matter and energy become interchangeable on a stellar scale. The gravitational wave detectors register a new pattern as the shock wave interacts with the star's complex internal structure. Each time the wave encounters a boundary between different layers of stellar material, it generates gravitational waves with characteristic frequencies that provide information about the star's internal composition. You realize that you're receiving a kind of seismic readout of the star's interior as it's being destroyed from within. Your instruments detect the formation of exotic matter states in the star's core as densities and pressures exceed anything that exists elsewhere in the universe. The core has become a neutron star, a city-sized object containing more mass than our sun, where matter exists in forms that can't be studied in Earth-based laboratories. The gravitational field of this neutron star is so intense that it noticeably affects the path of light passing near it. You feel the ship lurch slightly as the autopilot adjusts course to avoid debris accelerated by HD 2000. 847's changing gravitational field. The star's violent death throes are affecting the trajectories of objects throughout the surrounding stellar system, creating a chaotic and dangerous environment where previous navigational calculations no longer apply. The electromagnetic emissions from HD 2847 suddenly shift to frequencies associated with nuclear processes that shouldn't be possible under any natural conditions. You're detecting evidence of element formation through rapid neutron capture, the process that creates the heaviest elements in the periodic table. The star is literally forging gold, platinum, and other precious metals in quantities that exceed the total mass of rocky planets. Through the ship's most sensitive detectors, you observe the formation of exotic particles with properties that push the boundaries of the standard model of particle physics. The extreme conditions in the collapsing star core are creating particle interactions that occur nowhere else in the universe, providing a natural laboratory for testing theories about fundamental forces and the nature of matter itself. You notice that the star's rotation has accelerated to the point where its equatorial velocity approaches a significant fraction of the speed of light. This rotation rate would tear apart any normal object, but the immense gravitational field of the collapsing core holds the stellar material together even under these extreme conditions. The rotational energy alone is equivalent to the total mass energy of thousands of Earth-sized planets. The ship's seismometers detect gravitational waves with frequencies that indicate the formation of accretion streams as material falls toward the neutron star core. These streams of infalling matter reach temperatures of hundreds of millions of degrees and emit X-rays so intense that they ionize surrounding gases hundreds of kilometers away from the accretion streams themselves. You receive the last transmission from a monitoring probe positioned at 30O from the star. The probe reports that HD 2847's luminosity has increased by a factor of 10 billion in the last few minutes, and surface temperatures are climbing toward 100,000 Kelvin. The transmission ends abruptly as the probe is presumably vaporized by the intense radiation flux from the exploding star. Dr. Chen shows you calculations indicating that the shock wave has now reached HD 2847's photosphere and is beginning to accelerate the star's outer layers to escape velocity. The explosion proper is about to begin, and you realize that you have perhaps 6 hours before the expanding shell of stellar debris and high-energy radiation reaches your position 50O away. You feel a profound sense of isolation as you realize that you're about to become the closest human observers of a supernova explosion in recorded history. The nearest previous supernova observation was thousands of light years away, but you're experiencing this event from a distance measured in light hours rather than light years. The scientific value of your observations is incalculable, assuming you survived to transmit them back to Earth. The star's magnetic field undergoes a final catastrophic reconfiguration as the shock wave disrupts the field structure that has contained the stellar plasma for millions of years. The magnetic field lines snap and reconnect explosively, releasing magnetic energy equivalent to the rest mass energy of entire planets. These magnetic reconnection events accelerate particles to velocities approaching the speed of light. You observe through the telescopes that HD 2847's surface is now glowing with a brilliance that makes it painful to look at even through heavily filtered optics. The star has become a point source of light visible from thousands of light years away, outshining entire galaxies for brief periods. The energy output is so enormous that it noticeably heats the ship's hull, despite the tremendous distance. Your radiation detectors register a sharp increase in cosmic ray flux as high-energy particles, accelerated by the star's magnetic field, begin reaching your location. These cosmic rays have energies far exceeding anything produced by human particle accelerators, and they're numerous enough to pose a significant radiation hazard. Despite your ship's heavy shielding, the gravitational wave signature suddenly changes to a pattern associated with matter. Falling into a black hole, you realize with growing horror that HD 2847's the gravitational field is now so intense that not even light can escape from the core region, and matter falling toward the black hole is being accelerated to relativistic velocities. You feel the ship's hull vibrate as gravitational waves, with frequencies in the infrasonic range, pass through your location. These low-frequency gravitational waves are generated by the orbital motion of material spiraling into the newly formed black hole, and their wavelengths are comparable to the size of planetary systems. The fact that you can physically feel these space-time distortions emphasizes the incredible energies involved in the star's death. Through the communication system, you attempt to contact Earth to report your observations, but the intense electromagnetic radiation from HD 2847 is interfering with long-range communication. You're effectively cut off from the rest of humanity, alone with your colleagues, in the path of a cosmic catastrophe that will reshape the surrounding region of space for millions of years to come. The stellar debris expanding outward from HD 2847 begins to interact with the interstellar medium, creating shock waves that heat the surrounding gas to millions of degrees and accelerate it to supersonic velocity. You're witnessing the birth of a supernova remnant, an expanding bubble of hot gas and high-energy particles that will continue growing for thousands of years. Dr. Chen's analysis of the explosion dynamics indicates that the expanding stellar debris will reach your position traveling at approximately 30,000 kilometers per second. Dr. Childs, at this velocity, even microscopic particles carry enormous kinetic energy, and the ship's hull will be subjected to bombardment equivalent to a continuous nuclear explosion. You begin to understand why survival at this range is considered impossible. You observe that the newly formed black hole is accreting matter from the exploding star's outer layers, creating an accretion disk that glows with X-ray and gamma-ray emissions, intense enough to sterilize planets hundreds of light years away. The accretion process is so violent that it ejects narrow beams of relativistic particles along the black hole's rotation axis. Jets that could destroy anything in their path across galactic distances. The ship's AI begins implementing emergency protocols as it calculates the arrival time of various components of the explosion. The first high-energy photons will arrive traveling at light speed, followed by the fastest-moving stellar debris, then the main shell of expanding material, and finally, the slower-moving heavy elements forged in the star's core during its final moments. You feel a strange mixture of scientific fascination and primal fear as you realize you're about to experience forces that typically exist only in the centers of galaxies, or during the first moments after the Big Bang. The temperatures, pressures, and energy densities involved in HD 1847's explosion exceed those found in any other natural phenomenon, except perhaps the formation of the universe itself. Through the telescopes, you watch as the star's outer layers are completely ejected into space, revealing the incredibly hot, shock-heated interior. The exposed stellar core glows with a temperature of over 1 billion degrees, hot enough to emit gamma rays that can penetrate through meters of lead shielding. You realize that you're looking directly at nuclear fire unleashed on a stellar scale. Your instruments detect the formation of heavy elements through processes that don't occur anywhere else in the universe. The neutron-rich environment created by the core collapse allows for rapid neutron capture. Building elements heavier than iron through a process called the R process. You're witnessing the cosmic forge that creates the rarest and most valuable elements in the periodic table. The gravitational effects of the explosion begin to influence your ship's trajectory more significantly. The rapidly changing mass distribution as stellar material expands outward creates time-varying gravitational fields that stress your ship's hull and require constant course corrections. You realize that the explosion is literally reshaping the geometry of space-time in your region of the galaxy. Dr. Chen points out that the energy release from HD 2847's explosion is equivalent to the total energy output of billions of stars over their entire lifetimes, all concentrated into a period of seconds or minutes. This energy is sufficient to accelerate stellar debris to velocities that will carry it across interstellar distances, seeding nearby star systems with the heavy elements necessary for planet formation and life. You observe jets of relativistic plasma being expelled from the vicinity of the black hole at velocities approaching 99% of the speed of light. These jets carry away enormous amounts of energy and angular momentum from the black hole system, and they're narrow enough that their destruction extends across galactic distances. Fortunately, neither jet appears to be pointed directly toward your location. The electromagnetic pulse from the explosion begins to affect your ship's electronic systems, despite heavy shielding and hardening against cosmic radiation. You feel grateful for the redundant systems and manual backups as primary computers begin experiencing interference from the intense radio and microwave emissions generated by the expanding shock front. Through spectroscopic analysis, you detect evidence of exotic nuclear processes that create isotopes with neutron-to-proton ratios far from the valley of stable nuclei. Many of these isotopes have never been observed before and exist only in the extreme neutron flux environment created during supernova explosions. You're witnessing nuclear alchemy on a scale that transforms stellar mass quantities of ordinary matter into exotic nuclear species. You realize that the explosion has created a natural particle accelerator more powerful than anything humans could ever build. Charged particles are being accelerated to energies approaching the theoretical maximum possible in the universe, creating cosmic rays that will travel across galactic distances and influence the evolution of distant star systems for millions of years. The ship's radiation detectors begin registering gamma-ray bursts with energies so high that they create electron-positron pairs when they interact with the ship's hull. You're experiencing radiation at energy levels that literally create matter and antimatter from pure energy, demonstrating Einstein's mass-energy equivalence on a macroscopic scale. As the hours pass, you watch the expanding shell of stellar debris grow larger and brighter as it approaches your position. The debris front now subtends a significant fraction of your field of view, appearing as a brilliant, expanding ring of light that grows visibly larger with each passing minute. You realize that you're about to be engulfed by the physical remains of what was once a star 40 times more massive than our sun. You feel the ship begin to vibrate more noticeably as the first high-velocity particles from the explosion reach your location. These particles, accelerated to nearly the speed of light by the explosion's magnetic fields, precede the main debris shell by several hours, but carry enough energy to begin heating your ship's hull and stressing its structural components. Dr. Chen's final calculations indicate that when the main shock front reaches your position, your ship will be subjected to pressures equivalent to being at the bottom of an ocean millions of kilometers deep, temperatures comparable to the center of the sun, and radiation fluxes that exceed the surface of the exploding star itself. You understand now why the mission planners considered this a one-way journey. No technology could protect you from such extreme conditions. Through the ship's final telescope observations before the instruments are overwhelmed by radiation, you see that HD 2847 has become completely unrecognizable. What was once a stable, massive star has become an expanding cloud of glowing gas centered on an invisible black hole. The transformation is so complete that no trace remains of the original stellar structure. You take one last look at the approaching wall of stellar debris, now filling most of your field of view and glowing with the combined light of nuclear fusion, shock heating, and radioactive decay. In a few more hours, this expanding shell of cosmic destruction will reach your location, and you will become part of the explosion that will enrich the surrounding interstellar medium with heavy elements for millions of years to come. As the final systems begin to fail under the increasing radiation bombardment, you realize that your mission has succeeded beyond all expectations. The data you've collected will revolutionize humanity's understanding of stellar evolution, nuclear physics, and the violent processes that shape galactic evolution. Your sacrifice will advance scientific knowledge in ways that may ultimately benefit countless future generations. The expanding debris front continues to grow larger and brighter, and you prepare yourself for an experience that no human has ever survived: direct immersion in the expanding shockwave of a supernova explosion. You understand that in the next few hours, you will witness the ultimate demonstration of why stellar death represents both the most creative and destructive force in the universe. As the matter that composed a massive star is scattered across light years of space to eventually form new stars, planets, and perhaps even life itself, you feel the ship's hull begin to buckle and groan under the increasing pressure from the relativistic particles streaming ahead of the main shock front. The radiation levels have climbed beyond the capacity of your dosimeters to measure, and you know that every cell in your body is being bombarded by high-energy photons and particles that are systematically destroying your DNA and cellular structure. Dr. Chen collapses beside you, her body unable to cope with the massive radiation dose despite the ship's heavy shielding. You kneel beside her and see that her skin has already begun to show the telltale reddening of severe radiation poisoning. Her eyes meet yours, and you see both fear and wonder in her expression as she realizes that she's experiencing something no human has ever witnessed before. The ship's emergency lighting fails as the electrical systems are overwhelmed by electromagnetic pulses from the approaching shock front. You're now illuminated only by the brilliant glow streaming through the viewport from the expanding supernova remnant. The light is so intense that it's painful to look at directly, and you realize that you're being bathed in radiation that would instantly blind anyone not protected by the ship's filtered viewing systems. You help Dr. Chen to the medical bay, knowing that there's nothing the automated systems can do for radiation exposure of this magnitude, but wanting to make her as comfortable as possible during her final hour. The ship's medical AI confirms what you already know. The radiation dose you've both received would be fatal, even with the best medical treatment available on Earth. Through the ship's internal communication system, you hear reports from other crew members in various parts of the vessel. The engineering section reports that the main power core is experiencing instabilities due to radiation-induced changes in its control systems. The navigation section reports that all external sensors have been overwhelmed or destroyed by the intense electromagnetic radiation from the supernova. You make your way back to the observation deck, feeling increasingly weak, but determined to witness every moment of this unprecedented event. The expanding debris front now fills your entire field of view, a wall of brilliant plasma moving toward you at 30,000 kilometers per second. You calculate that it will reach your position in approximately 2 hours. The ship's structural sensors report that the hull is beginning to sublime, literally evaporating under the intense radiation bombardment. The neutronium composite materials that were supposed to protect against the most extreme cosmic environments are being destroyed at the molecular level by gamma rays with energies exceeding anything in the ship designer's specifications. You feel the artificial gravity fluctuate and then fail completely as the ship's power systems are overwhelmed by electromagnetic interference. You float freely in the observation deck, tethered only by safety lines, watching the approaching wall of stellar destruction that will soon engulf you completely. Through the ship's final functioning radio equipment, you attempt to transmit your last observations back to Earth. Knowing that the data will take years to travel across the light years, separating you from home, you describe the incredible beauty and terror of watching a star die, the overwhelming scale of the forces involved, and your growing understanding of why no form of life could survive at close range to such an event. The temperature inside the ship begins to rise noticeably as the hull absorbs increasing amounts of high-energy radiation. The life support systems struggle to maintain habitable conditions, but you know that they're fighting a losing battle against the physics of stellar explosion. The energy flux you're experiencing exceeds the design limits of any conceivable technology. You observe through the remaining functional sensors that the expanding supernova remnant has begun to interact with nearby interstellar gas clouds, creating brilliant shock-heated regions that glow in X-rays and ultraviolet light. These interaction regions are forming the seeds of future star formation, as the shock waves compress interstellar gas to densities sufficient to trigger gravitational collapse. Dr. Chen's condition deteriorates rapidly, and you realize that she has only minutes left to live. She manages to whisper her final scientific observations about the exotic nuclear processes visible in the spectroscopic data, contributing to human knowledge even as the radiation destroys her body. You feel honored to be with her during these final moments of discovery. The ship's hull begins to glow red hot as it absorbs increasing amounts of thermal radiation from the approaching shock front. You can feel the heat through the deck plating, and you know that the interior temperature will soon become incompatible with life. The ship is being transformed into a furnace by the energy released during HD 2847's death. Through the communication system, you hear the final reports from your remaining crewmates. The chief engineer reports that the reactor containment is beginning to fail under the extreme conditions and recommends immediate evacuation. A darkly ironic suggestion, given that there's nowhere to evacuate to in the path of a supernova explosion. You watch in fascination as the expanding debris front begins to show internal structure. Dense knots of heavy elements created during the star's final moments of nucleosynthesis, surrounded by more diffuse clouds of lighter elements from the star's outer layers. You're witnessing the cosmic recycling process that will eventually lead to new star systems, enriched with the materials necessary for rocky planet formation. The radiation levels inside the ship climb beyond anything you thought possible for a shielded environment. Your personal dosimeter has long since saturated, but the ship's remaining instruments suggest that you're receiving radiation doses equivalent to standing next to an unshielded nuclear reactor. The biological effects are catastrophic, but somehow your consciousness remains clear enough to continue observing. You feel your body beginning to fail as the massive radiation dose overwhelms your cellular repair mechanisms. Your vision becomes blurry, your coordination deteriorates, and you experience the onset of radiation sickness symptoms that would normally take days or weeks to develop. The intensity of the radiation is compressing the entire pathology of radiation poisoning into a matter of hours. Through the ship's final telescope, you observe that the supernova has become visible across interstellar distances. Stars in nearby systems are being illuminated by light from HD 2847's explosion. And we are now seeing the brilliant new star that has appeared in their night sky. Satan. The ship's artificial intelligence makes its final report, describing the systematic failure of all major systems under conditions far exceeding their design specifications. The AI calculates that the ship will be completely destroyed within 90 minutes, vaporized by temperatures and pressures that exceed those found in the cores of massive stars. You manage to record one final personal message, describing your awe at witnessing one of the universe's most spectacular phenomena despite the tragic circumstances. You express hope that the data you've collected will advance humanity's understanding of stellar evolution and perhaps lead to better protection for future deep space missions, though you doubt anyone will ever again attempt to observe a supernova at such close range. The expanding shock front begins to fill your entire field of view, a brilliant wall of plasma and debris moving at a significant fraction of the speed of light. You can now see individual clumps of material within the expanding shell, some containing more mass than entire planetary systems, all moving at velocities that would carry them across galactic distances. You feel the ship begin to tumble as its attitude control systems fail under the electromagnetic interference from the supernova. The sensation of rotation combines with your radiation sickness symptoms to create severe nausea, but you force yourself to continue observing through the viewport as the cosmic catastrophe approaches. The hull temperature climbs above the melting point of most metals, and you watch sections of the ship's outer structure begin to deform and flow like liquid. The neutronium composite materials that were supposed to be nearly indestructible are being reduced to plasma by the intensity of the supernova's radiation. Through the ship's seismometers, you detect the arrival of gravitational waves from the explosion's interaction with nearby matter concentrations. The waves are strong enough to create measurable oscillations in the ship's structure, and you realize that you're feeling the direct effects of space-time distortions created by one of the most violent events in the universe. Your remaining crewmates succumb one by one to the extreme radiation exposure, and you find yourself alone in the observation deck, the last conscious witness to humanity's closest encounter with stellar death. Despite your own deteriorating condition, you feel a profound sense of privilege at being chosen by fate to witness this cosmic spectacle. The ship's power core finally fails completely, plunging you into darkness except for the brilliant glow from the approaching supernova rim. The silence is profound. No hum of machinery, no whisper of life support systems. Just the cosmic violence visible through the viewport and the sound of your own labored breathing. You use the ship's emergency beacon to transmit a final data burst toward Earth, containing compressed versions of your most important observations. The transmission will travel at light speed across the dozens of light years separating you from home, carrying with it the last testimony of humans who dared to look directly into the face of stellar death. The expanding debris front continues to grow larger and more brilliant, and you begin to make out incredible details in its structure. Rivers of molten heavy elements flow through clouds of lighter gases, while magnetic fields channel streams of charged particles into complex, beautiful patterns that span distances comparable to entire solar systems. You feel your consciousness beginning to fade as the radiation damage to your nervous system becomes overwhelming. Your vision dims, but somehow the brilliant light from the supernova penetrates even through your closing eyelids. You realize that this cosmic fire will be the last thing you ever see, and you feel strangely honored by the beauty and terrible majesty of your final sight. The ship's hull begins to buckle inward as the pressure wave preceding the main shock front reaches your location. The structural failure happens gradually at first, then accelerates as the hull materials lose their molecular cohesion under the extreme conditions. You watch sections of bulkhead begin to glow and flow like lava. Through your fading awareness, you sense rather than see the moment when the main shock front finally reaches your position. The sensation is indescribable, like being struck by a mountain moving at the speed of sound, or being immersed in the heart of a nuclear explosion. Every atom in your body is suddenly subjected to forces that tear apart the very bonds holding matter together. In your final moments of consciousness, you experience a strange clarity as your brain's dying neurons fire in complex patterns triggered by the exotic radiation environment. You understand. With crystalline precision, exactly why survival at this range is impossible. The energy densities involved exceed the binding forces that hold ordinary matter in stable configurations. The ship disintegrates around you, its constituent atoms scattered and ionized by temperatures exceeding those in stellar cores. You become part of the expanding supernova remnant, your body's elements mixed with those forged in HD 2847's final moments of nuclear fusion. The carbon in your cells, the oxygen in your blood, the calcium in your bones, all become part of the cosmic enrichment process that will seed future star systems with heavy elements. Your consciousness fades as your neural networks are disrupted by the extreme conditions. But in some strange sense, you become part of something larger and more magnificent than individual existence. Your atoms join the expanding cloud of stellar debris that will travel across interstellar space for thousands of years, eventually becoming incorporated into new stars, planets, and perhaps even new forms of life. The data you transmitted toward Earth becomes your scientific legacy, carrying detailed observations of supernova physics that will revolutionize astronomy for generations. Future scientists will study your measurements to understand the nuclear processes that create heavy elements, the shock wave dynamics that distribute stellar material across galactic distances, and the extreme physics that governs the deaths of massive stars. Years later, as your final data transmission reaches Earth, astronomers there observe HD 2847's supernova as a brilliant new star in their night sky. The explosion is visible to the naked eye despite its tremendous distance, confirming the incredible energy release that you witnessed firsthand. Your sacrifice has provided humanity with unprecedented insights into one of the universe's most fundamental processes. The expanding supernova remnant continues to grow and evolve over the following centuries. The shock waves you experienced propagate through the interstellar medium, compressing gas clouds and triggering the formation of new stars. Some of these stars will form planetary systems enriched with the heavy elements created during HD 2847's death. Elements that your body helped to distribute throughout the cosmos. Decades after the explosion, the neutron star or black hole that formed from HD 2847's collapsed core begins to interact with nearby matter, creating high-energy phenomena that are detectable across galactic distances. The exotic object serves as a natural laboratory for testing theories about the most extreme states of matter and the strongest gravitational fields in the universe. The supernova remnant gradually cools and expands over thousands of years, but its influence on the surrounding region of the galaxy persists for much longer. The heavy elements it distributed seed the formation of rocky planets in nearby star systems, while the shock waves continue to trigger star formation in molecular clouds dozens of light years away from the original explosion site. Eventually, the atoms that once composed your body and your spacecraft become incorporated into new celestial objects, perhaps the core of a rocky planet orbiting a young star, where they might someday become part of new forms of life that evolved in an environment enriched by HD 2847's depth. Your sacrifice becomes part of the cosmic cycle that connects stellar death to the emergence of complexity and life in the universe. Future civilizations that develop in star systems enriched by HD 2847's supernova will owe their existence partly to the nuclear processes you witnessed during the star's final months. The gold in their electronics, the uranium in their rocks, the rare earth elements that enable their technology, all were forged in the stellar furnace whose death you observed at impossibly close range. Your story becomes part of the scientific record that guides humanity's understanding of stellar evolution and the cosmic processes that shape galactic evolution. The measurements you made during your final hours provide crucial data about supernova physics that cannot be obtained through distant observations, advancing human knowledge in ways that benefit countless future generations. The mission that cost your life establishes important principles for future deep space exploration, demonstrating both the incredible scientific value of close-range observations and the absolute necessity of respecting the fundamental limits imposed by extreme cosmic phenomena. Your sacrifice helps define the boundaries between achievable exploration and cosmic forces too powerful for any conceivable technology to overcome. In the decades following your death, advances in physics, inspired partly by your observations, lead to new theories about the relationship between matter, energy, and space-time. Energy and space-time under extreme conditions. Scientists develop better models of supernova explosions, neutron star formation, and the nucleosynthesis processes that create heavy elements in stellar cores. The communication protocols you established during your final hours become templates for future missions to observe cosmic phenomena at close range. Your methods for data compression and transmission under extreme electromagnetic interference conditions save critical scientific information. In subsequent missions that encounter similarly hostile environments, your experience demonstrates that while humans cannot physically survive exposure to the most extreme cosmic phenomena, human consciousness and scientific curiosity can push the boundaries of knowledge even in the face of certain death. Your willingness to observe and record data during your final hours exemplifies the scientific spirit that drives humanity's exploration of the universe. The legacy of your observations extends far beyond the immediate scientific data you collected. Your story inspires future generations of scientists and explorers, demonstrating that the pursuit of knowledge can give meaning to existence even under the most extreme and hopeless circumstances. Your sacrifice becomes a symbol of humanity's commitment to understanding the universe, regardless of personal cost. Centuries later, as humanity develops more advanced space exploration capabilities, your mission is remembered as a crucial milestone in the species' growing understanding of cosmic phenomena. The data you collected during HD 2847's explosion continues to inform theoretical models and guide the design of new instruments. For studying stellar evolution, the supernova you witnessed becomes a landmark in astronomical research, with generations of scientists studying its evolution and using your close-range observations to test and refine their theories about stellar death. Hey D. 147's explosion serves as a natural experiment that could never be replicated in any laboratory, making your data invaluable for understanding the physics of extreme environments. Your atoms, now scattered across light years of space, as part of the expanding supernova remnant, carry with them the information content of your observations and experiences. In some philosophical sense, your knowledge becomes part of the cosmic information structure, contributing to the universe's growing complexity and organization. The philosophical implications of your experience resonate through human culture for generations. Your confrontation with cosmic forces infinitely larger than human scale provides insights into humanity's place in the universe and the relationship between individual consciousness and cosmic processes. Your story becomes part of the intellectual framework through which humans understand their cosmic context. Future space missions adopt safety protocols based partly on the lessons learned from your fatal encounter with HD 2000 explosion. While no technology can protect against the extreme conditions you experienced, better understanding of supernova physics allows future explorers to position themselves at safe distances while still obtaining valuable scientific data. The heavy elements created during HD 2847's explosion, and distributed by the shock waves you experienced eventually become incorporated into new planetary systems throughout your region of the galaxy. These elements enable the formation of complex chemistry and potentially life itself, making your witnessing of the star's death part of the cosmic process that creates the conditions necessary for future biological evolution. Your sacrifice ultimately demonstrates that while individual human lives are brief and fragile compared to cosmic timescales, human consciousness has the unique ability to comprehend and find meaning in the most extreme cosmic phenomena. Your observations of HD 2847's death contribute to the universe's growing self-awareness through human scientific understanding. In the end, your experience at HD 2847 embodies the fundamental truth that stellar death represents both destruction and creation on the grandest possible scale. Your atoms become part of the cosmic recycling process that transforms stellar cores into the building blocks of future worlds. While your observations advance human understanding of the nuclear processes that shape galactic evolution and enable the existence of life itself,